So with that, I think I'm going to start here. So we're going to talk about total sulfur analysis, and hopefully I was so grateful when I posted this on LinkedIn and a couple of people recognized at least that, yes, we are talking about an old Leonard Skinner song here. But, you know, we talk about that because, of course, sulfur is ubiquitously known for the fact that it has a strong smell to it. So that was kind of where that analogy came up from. So the specific total sulfur analyzer we're going to be talking about is from a company called Atom Instruments. And I'm going to talk a little bit about the different ways that are available to measure total sulfur, and then, of course, focus a little bit on what's kind of unique about them. So I'm going to start this off, as I always do, with a little bit about who we are, and then we'll talk about Atom Instruments and total sulfur and how they implement this measurement in the field. Insight Analytical is a Calgary-based systems integrator and distributor. We work at a fairly large shop in the northeast of Calgary, about 20,000 square feet of manufacturing space available, a lot of bay doors, big 10-ton overhead crane, bring a full analyzer building straight into the shop off the back of a flatbed. For the Canadians, we're an AB 83 compliant fabricator. So everything that we can put out, or that we put out, can have a CRN on it. For Europeans, that's kind of the equivalent of the Pressure Equipment Directive, special set of pressure registrations for Canada. A lot of the people here have worked with me for a long time, from the Western Research days, from the Amatech days, from other companies I've been involved with. And so bring together a group of people that really have some great skill sets. You know, we have a really good document control person. We have great drafting skills. One of the draftsmen that works with us has been doing analyzer buildings and shelters and analyzer installations for probably 30 years now or so of drafting those. So work with journeyman electricians, run full factory acceptance tests right out here in Calgary. We have a full set of systems integration capabilities, everything from custom sample systems to process analyzer integration to PLCs and automation, full analyzer buildings. Some of you may know me from also teaching a course on how to design analyzer sample systems. I was excited. I saw a post go up on LinkedIn today that I might actually get to go to the Netherlands in late September and actually teach one in person. I'm doing them all by Zoom lately, and it's a long time to teach. We will do everything from front-end engineering analysis, we're working on a couple of feed projects right now, to full detail engineering, to, of course, systems fabrication, installation and commissioning, and we're really happy to run a full service team. We have service out of Calgary, out of Grand Prairie, out of Edmonton. Really thrilled. We have a new person starting with us soon, Saul Dixon, who's going to be coming in on the service group as well. So it's one of probably our fastest growing groups. So I want to start off a little bit about talking about, you know, why do we even concern ourselves with measuring total sulfur? Sulfur is the 10th most common element on the planet. And it's really common in hydrocarbon streams. Basically, you know, if you think about any living creature, be it plant or animal, we all have sulfur in it because it's all part of the DNA. Amino acids like cysteine and that are sulfur compounds. And so when we have hydrocarbons that have been produced from essentially decaying organisms, those all end up with sulfur in them as well. So sulfur is really common in all the hydrocarbons we produce, but sulfur also creates a number of issues in itself. Many of the sulfur compounds are corrosive, so we have a concern about measuring sulfur because of the potential corrosion impacts of it. We have concerns about it in regards to toxicity, you know, especially with things like H2S, CS2. We have concerns that when we burn these hydrocarbons, they're going to release things like sulfur dioxide to the atmosphere. So we have concerns about SO2 pollution. Sulfur is particularly reactive. And so many times if we have catalyst beds, sulfur likes to go and react with those catalytic materials and can deactivate our catalysts. And then finally, of course, we have things like custody transfer agreements, where if I'm selling oil or propane or natural gas to another person, he doesn't want to take my sulfur. So we have an agreement about how much we're allowed in there. So we want to measure it to know how much, whether we're meeting those specifications. We talk about a lot in the oil and gas industry and refining applications, but it's important to pharmaceuticals and beverages as well. So, there's many, many parts of the industry where we'd like to be able to make a sulfur measurement. It's not always an easy thing to deal with, though. Sulfur has some unique chemical properties. And so, if you got my emails, they were called fire and brimstone because, of course, sulfur is associated with hell. And of course, that's where most analyzer technicians feel like they are when they're trying to work on some of their sulfur analyzers. Sulfur has a lot of, sulfur compounds have a lot of interesting properties to them. Like we said, a lot of them are toxic. Things like H2S and CS2. A lot of them are flammable. CS2 especially could be considered, we often see a need to meet special hazardous area requirements. There's going to be large concentrations of CS2 there because it's so easy to ignite. Sulfur compounds can be difficult to deal with. They like to absorb and stick on surfaces. So when we're talking about sample transport lines or sample systems, we can run into issues with not being able to get those sulfur compounds over to our analyzers very easily. And then elemental sulfur itself has some weird properties. Most chemicals, when you heat them up, they become less viscous. Elemental sulfur goes the other way around. When you start, you get it to melt, the viscosity decreases for a while as you heat it up, and then suddenly the viscosity shoots up to the roof. So it can be difficult to get things like elemental sulfur to transport. Of course, we all know them as being smelly, H2S with the smell of rotten eggs, but things like mercaptans and thiols, all the sulfur compounds tend to be, because they're reactive, they react to those little olfactory sensors that we have. And they can be difficult to measure. They can either be difficult to measure because to a lot of the measurement principles, they look similar, or they become difficult to measure because it's hard to get them into the analyzer, or not all analyzers measure them equally as well. So there's a whole bunch of different techniques that we use to try to measure total sulfur or sulfur compounds in systems. So how do we measure it? Well, that's part of the problem. We're left with this big decision to make. We have all these different possible measurement techniques, from chromatography. If it's high concentration, we might try to do that with a TCD detector. If it's the lower concentrations, we might try to do that with a flame photometric detector. There'll be people who try to do it by ultraviolet absorption. But again, some of those sulfur species overlap each other so much they become hard to separate. We can measure them by X-ray transmission. We can measure them by X-ray fluorescence. One of the common methods that we try to measure them is with lead acetate tape. But if we want to do total sulfur, we have to use pyrolysis with that. Some people have looked at using mass spectrometry on flare lines and things like that to do total sulfur measurements. So there's a whole bunch of different ways to do it. The one we're going to spend our time talking about today is doing it by UV fluorescence. And there's some particular advantages, especially in certain applications, to using this methodology. For one, similar to the lead acetate tape approach, it provides a direct measurement of all the sulfur compounds. In the lead acetate tape approach, they convert it to H2S. In the UV fluorescence measurement, what we do is we combust all the sulfur species, convert them to SO2, and measure all the SO2 that we produce. So I compare that then to things like trying to do it with a GC, where we're going to try to measure individual components and see if they all add up. The fluorescence method is nice because we convert everything to SO2 and measure just that one species. It's applicable to both gases and liquids. So again, another convenient thing about it, we can use the same sort of technology to do gases and liquids. Has a particularly wide dynamic range. We're going to talk about how in flare applications, we can go from 0 to 100% H2S with often detection limits down in the tens or hundreds of ppm. It's reliable, low maintenance, and it's the subject of some ASTM and ISO standards. So is a standard method for doing things like total sulfur in propane, total sulfur in gasoline, total sulfur in diesel. So let's talk a bit about how it works. So as we kind of mentioned, the basis behind this is that we're going to want to measure SO2. So what we do is we take our hydrocarbon stream or wherever we want to measure our sulfur species in, we add some oxygen into it, either by adding air or adding molecular oxygen. We add oxygen to the stream. We heat it up. We run it through a furnace that runs, in the atom case, I think it's 1150 degrees C. It's either 1050 or 1150. We take the stream, we heat it all up. We have the oxygen in there. It oxidizes everything. The carbons in that sulfur compound go to CO2. The hydrogens in that sulfur compound react with the oxygen and go to water. But the thing that we're interested in, the sulfur, it goes on and makes sulfur dioxide. So now we've taken that stream, and if there's other hydrocarbons there, just makes more CO2 and more water vapor. But all of the sulfur atoms are going to get converted to sulfur dioxide molecules. So we're going to have a one-to-one correspondent. We'll make as many correspondents. We'll make as many sulfur dioxide molecules as we had sulfur atoms in the original compound. We do make a lot of water, though, and water vapor can be problematic for us if it condenses out. So we have to deal with the water. So the second step of this process is to dry that sample. And we use a permeation type dryer. Often these are a Nafion membrane. So Nafion is I think it was a DuPont thing. The chemical is originally developed by DuPont, I believe. It's kind of like a Teflon, but it has sulfonic acid groups in it. And the sulfonic acid groups allow it to absorb water into it easily and pass water right across the membrane. So we can bring our stream that came from that oxidizer, we can bring that stream in, and just like in a countercurrent heat exchanger, run dry gas through the other side of the membrane and transport the water right across the membrane and dry that gas out before we go into the analysis. Couple of advantages of it. If we let liquid water condense, like we might in a chiller type dryer, we can have problems with chemicals absorbing into the water. The permeation dryers are especially good for being able to remove the water from the stream, but not bias any of our other measurements or chemicals along the way. So now we've taken it, we've oxidized the stream, we made everything at SO2, we remove the water so we can transport the sample easily, and we take it over to an ultraviolet fluorescence detector. Sulfur dioxide absorbs ultraviolet light. When it does, it moves up into a higher energy state. It's not stable up there in that state. So it rattles around for a few microseconds and then says, oh, I got to give up some of this energy. It gives off a photon. When it gives off that extra photon, we say that it's fluoresced. And that photon comes off at a different wavelength than the one that came in. So now if we just count the photons or measure how many photons are coming off, put a photo detector in there, we have our sample is sitting in here. The beam of ultraviolet light hit the sample. It gives off photons that we pick up at the photo detector. From the photocurrent we see here, how many photoelectrons get made at the detector, we can estimate the sulfur dioxide concentration. Can be a very sensitive method for doing this. This technology is used at the parts per billion level in ambient SO2 monitoring. So how much SO2 is in the ambient air in our city or things like that. Very sensitive, very well-established technique, been around for a long time. So if we want to put the whole system all together, we bring our sample in. We bring some air and oxygen into a high temperature furnace. So it is 1050, there we go. That's my correction. We bring it into that 1050 degrees C furnace. We cook everything in there. We convert the sulfur dioxide to, or the inlet sulfur to sulfur dioxide. We run it through that dryer, and then we take the sample that comes out of the dryer into the fluorescence cell and measure the amount of SO2 that's in there. This is the unique part about ATOM. They're the only people that use what's called an excimer, a special type of ultraviolet light source. So this is kind of, as I put it, this is where the magic happens. They use this special light source because it gives them a bunch of improvements, if you like, in how they're able to do the detection. We're going to talk about those in a minute. First, we want to talk about this word, fluorescence. So when we talk about the fluorescence of sulfur dioxide, the sulfur dioxide is in its ground state energy. It's in, sitting here, that's its basic energy, the energy it would have at the normal temperatures around. It gets hit by a photon of this ultraviolet light. That pumps it up to a higher energy level. When it goes to a higher energy level, it gets a different electron. The electron moves to a different orbital, an outer shell, and it changes a whole bunch of how the thing's vibrating and rotating. And so it can go through a bunch of non-radiative transitions that don't give off any photons. But eventually it gets to the point where it says, I just want to go back home. I just want to go back to my ground state. And when it drops down to that ground state, it gives off another photon of light. When we're talking about doing this with an excimer, this happens at around 222 nanometers. And we measure the light that gets emitted somewhere in the 280 to 300 nanometer range. So the wavelength of light changes substantially during the fluorescence. This is good because it lets us determine the difference between photons that were part of the excitation process, ones that came from the lamp, and photons that are produced by the chemical we want to measure. We just have to look and say, well, they should have really different energies. So the thing, all the stuff that happens over here, this is a function of how the SO2 molecule behaves. The thing that we can do to change how this process happens a bit is look at what type of a light source we're going to use. And the excimer has some advantages. It's really bright. It's really monochromatic. So the increased brightness gives us better sensitivity. Being really monochromatic gives us better linearity. Being at just the right wavelength makes a bit of a difference too. It helps us to separate the potential fluorescence of some other things. And excimers have long life compared to some of the other lamps that are used. So I'm going to talk just a bit about a couple of those features. One of the common ways to do this is with what's called a zinc lamp. Emits a line at 213.9 nanometers. And the thing about the zinc lamp is because of the light source variations, you end up with a bit more of a noisy baseline. When you compare the baseline there to what we see when we're using an excimer, the baseline's more stable. So we can tell where zero is a little bit more reliably. The other thing is the thing that makes that baseline wiggly also makes the peaks wiggle more. So when we do get some fluorescence, when we use something like an excimer, we get better data point or beta point repeatability, if you like. So the peak is more stable, more repeatable peaks, baseline is more stable. It gives us better detection limits. The other thing that it does, or the other advantage it potentially provides, is that a lot of systems that we're going to measure sulfur in, there'll also be nitrogen compounds there. And when we burn nitrogen, just like we went through that furnace, and we said, well, I'm going to take my S atoms and react them with oxygen, and that's going to make SO2. Well, when we have nitrogen in the system and we react it with oxygen, we can make nitric oxide, NO. And NO is an interferent. it fluoresces as well. And so if we use a wavelength of light that nitric oxide would like to absorb, then we're going to see the nitric oxide fluorescence as well. So we show the example up here when we do this with a zinc lamp. If we put in a bunch of nitric oxide in the system, we get a big peak that happens just, we think it's SO2. 500 ppm of nitric oxide, it turns out, would give us a bigger peak than 1 ppm of SO2 would give us. And remember, a lot of our chemical processing, we go through things to get rid of the sulfur in, say, our crude oil or our natural gas. We don't necessarily do any special processing to get rid of nitrogen compounds. So in this particular case, if there's a lot of nitrogen compounds there, we'll get a highly biased sulfur dioxide reading. We run exactly the same sort of thing using the Excimer lamp. And that peak that was bigger than the sulfur dioxide here becomes this tiny peak that we see over here. There's about a 20-25 times improvement in how much we can reject the impact of nitric oxides on our measurement. So it gives us better detection limits and gives us better sensitivity. So we're going to talk mostly about the online total sulfur analyzers. They also do a lab analyzer. But there's 4 flavors of the online analyzer, if you like. One for flare gas analysis, one for a generic sulfur and gas analyzer. It'd be the sort of thing that we'd use in natural gas or in LNGs. There's a number of different, multiple different applications, fuel gases, etc. If we want to go to this is typically used when the concentrations are greater than 1 ppm or so. If we want to go to less than 1 ppm, we look at the trace analyzer. And then the other one, which is especially interesting a lot of times, is the SLA, or the sulfur and liquids analyzer. And this will be used for gasoline and diesel, refined fuels, reformers and isomers, condensates, LPGs, things that are going to be difficult to make be vapors. We'll measure it directly as a liquid then. There are a number of standard test methods built around the use of UV fluorescence. So ASTM D5453 is the one that's commonly used for things like motor fuels and oils. So when we're talking about diesel and gasoline, this is kind of the specification that typically applies. If we're talking about things like natural gas, fuel gases, propane, the ASTM standard that's probably the most applicable for that one is ASTM D6667. And so those standards have specific performance requirements that you have to show that you meet. And the atom analyzers have been demonstrated to meet those performance requirements. If we start talking about things like benzene and aromatic hydrocarbons, there's a different ASTM standard, and ISO itself has a separate standard that's applied often for automotive fuels. Again, this is for things like gasoline and diesel. So there's different ASTM standards that we want to look for as well, and understand that the UV fluorescence method has been written into those standards. Gives it a bit of viability or validity, if you like, because it's part of the standard. Some of the features that we see in the atom analyzers: low maintenance operation, air only and not oxygen. This is important to us in a lot of applications just because having to handle high purity oxygen creates a whole bunch of other difficulties for us in our sample systems, in our safety requirements, etc. So some of the UV fluorescence analyzers that have been developed over time have used oxygen as a primary combustion source. It's nice when we can just use instrument air or bottled air. If we want to do that really trace measurement, though, if we're trying to get down into that parts per, 25, 50, 100 parts per billion kind of range, then the ATOM devices will go back to using bottled oxygen and argon as a carrier for that, just to get that extra degree of purity in the air source. They're fairly fast. Typical analysis is around typically 100 to 180 seconds. So about a minute, 1.5 minutes to 3 minutes. In that period of time, it's basically, there's periods of time between injections of the thing we want to measure into the detector, and then there's kind of a period of time where we wait. So in that duration, we're usually at 95 to 99% response to any change that's happened in the process. Support all the standard communication with protocols, reasonably compact footprint. We can put these into a shelter relatively easily. Like most analyzers, they require a custom sample system that is going to ensure that you get a representative sample over the analyzer. The sample system shown here is for a dual stream liquids analyzer, but different configurations are going to need a different sample system. Almost all online analyzers are going to need some type of sample system to condition that sample and make it appropriate for the analyzer. ATOM will provide sample systems directly, or of course, as an integrator, happy to manufacture them up here for you as well. There's separate sort of gas systems for the FGA, the flare gas analyzer, the typical gas analyzer, the standard gas analyzer, and the trace sulfur analyzers. And of course, liquid systems require some unique things as well. On the standard liquids analyzer, we will typically measure somewhere greater than 1 ppm by weight, with measurements ranges going all the way up to 10% by weight. So again, one of the beauties of this technology is it can have quite a wide dynamic range. So capable of being made a dual stream device, because the analyzer doesn't measure in ppm by weight, it really measures in ppm by volume. In order to deliver a ppm by weight number, we have to provide some real-time density correction. So we look for a densitometer in the system to provide the density of the fluid, and that lets us convert volume to weight. As I mentioned, we kind of do injections. So we get some counts or signals off the detector. And these are what repeat injections will tend to look like. This is running down around 8 ppm. So, these are very repeatable, excuse me, very repeatable injections on these devices. And what we do is with each injection, we look at what the peak height is. And from that, where peak area is, and calculate the concentration from that. And so here you see, multiple injections after each other, one after the next. This is at 6.8 ppm by weight in diesel. And we see the signals, quite repeatable. We're typically going to see 200 ppb, 0.2 ppm variations around those levels. So this is, again, consistent with ASTM D5453. This was the one that was related to things like measurement of sulfur in gasoline, diesel, jet fuel, condensates, etc. Naphthas, it's applicable to those sorts of applications. Without any averaging, we can get to about 2% of measured value, or 200 ppb, for a repeatability number. If we include some averaging there, we take a 5-minute average of those peaks, bring it down to about 100 ppb. And typical linearity will be about 2% of full scale. And that full scale may be going over 3 or 4 orders of magnitude. So we may be going from 10 ppm to say to 10,000 ppm. On the flare gas application side, and so this really came up big in the US with changes the EPA made, CFR 40, Part 60, Subpart JA, where they put a bunch of requirements on what we could put to flare and total sulfur in flares. And so we have to look at methodologies that we're going to be capable of measuring total sulfurs. And so the thing with a flare line is you may have almost no sulfur there most of the time. But then if one of your operating facilities, let's say your sulfur recovery unit, goes to flare, well, your flare concentrations may go up to all the way up to 50, 60, 70, 80% H2S. So one of the strengths, again, of this technology is the wide dynamic range it can operate over. So you can see here, we're showing a calibration curve, basically from 0 to 100% H2S. You get a nice linear relationship, and we can get repeatabilities down in the 50 parts per million while making those sorts of measurements. So we can take that measurement all the way, if we had a second curve on here, we could have a whole bunch of data points right down here in that 0 to 1% and be seeing 50 or 100 ppm sort of repeatability and measurements from there. Allows us to do that direct measurement of H2S in the flare lines, of the total H2S, along with the other sulfur species, because again, it might not be your sulfur plant that goes to flare. Maybe it's a Murox unit. And so really we're pumping a bunch of mercaptans into there. We want to be able to measure those total sulfur species regardless of what form they come in. That's what the regulation was written around. Doing it as a total sulfur measurement makes calibration a lot easier and uptime a lot easier as compared to trying to do it with a chromatograph. If we do it with a chromatograph and measure individual species, we have to calibrate for each one of those. So this process of oxidizing all the SO2 and saying I only have to measure one thing allows us to make that total sulfur measurement a lot easier. Of course, we lose the capability to measure the individual compounds. So we're going to look at what the requirements are for the application. The standard gas analyzer is typically used for applications where we have more than 1 part per million. Often more than, we can do it for natural gas in that 4 part per million range. If we want to go much lower than that, we're going to have to look at using a different version of this. So the SGA is designed really for gas phase applications where there's more than 1 ppm of total sulfurs there. It can operate all the way up to 100% sulfur species, but typically we're using this, in applications like natural gas processing, propane, LPG, a light butane stream that we can vaporize easily. These are all related back to that ASTM standard again, that ASTM D6667 standard. Analyzers, again, can be dual streamed. And if we look at the sort of data that we're able to do or see, this is on a vaporized butane stream that has methyl mercaptan in it. Speaking of service guys, there's my buddy Doug. Hey, Dougie. And Miss Dalzell has joined us, I see. So we're talking about this particular version of the analyzer, the SGA. We can be looking at applications like sulfur species and butane. So in this case, they were looking for methyl mercaptan. Sorry, I can't draw when the screen is zoomed. Frustrating. So about 9 ppm of mercaptan in an instrument grade butane stream. And you can see that we get a repeatability of around 100 parts per billion. 0.096 ppm would be 100 ppb. So measuring down at that 9 ppm level, we can see 100 ppb repeatability on those measurements. If we also take that and look at, how well do we do at different concentrations? So again, instrument grade butane going from 9 ppm down to 4.7 ppm, down to around 2.5 ppm, and then coming all the way down right around 0 at 20.23 ppm. We can see each step change that happens in the concentration. They take a little bit of time because when we're at that low of concentration, all these absorption, desorption effects come into play as well. It takes a while for things to stabilize out. But again, so great detection limits down in the low range. Like many analytical techniques, the lower the range is typically, the harder it is to do. So that's why we often like to show this. Hey, look, if I can do 9 ppm, I can probably do 90 ppm. I can easily do 900 ppm. So ranging up is usually easy. Ranging down is harder. So we tend to show this data about, look how good we do at low concentrations. The really great linearity of this technique helps that. And if we want to smooth things out, we can put a user-defined averaging in there. We can average from 1 scan, which is no averaging, up to 10 scans and set that up in the software to provide an average number. If we're not worried about response time as much, we can get a little bit more stable, noise-free number that way. If our goal is to go to really low concentrations, we go to the trace S. And this is typically for sulfur species less than 1 ppm. They can range up to about 100 ppm. So we lose that ability to go to really high concentrations, but we improve our ability to measure at low concentrations. When we do that, we use an oxygen-argon carrier gas for the combustion, gives us a bit better purity and stability on that oxidation source. Again, we can dual stream this. Still ends up being compliant with the ASTM standard, the ASTM 6667, but now we can get down to detection limits in the 50 or even 25 parts per billion. So again, and this is going to be really important in catalyst protection applications. If you're running something like an ammonia plant and you're bringing in product natural gas and you're trying to scrub all the H2S out of it with a zinc oxide absorber bed, and you want to know what's the concentration at the outlet of my zinc oxide bed because I want to protect my upstream catalysts. Well, now you're talking about needing detection limits down in these low parts per billion sort of levels. And so again, this is some data that was done around 200 parts per billion, sulfur dioxide and butane. And you can see that, at 200 parts per billion, the variability of this, whoops, I can't draw while I'm doing that, just moves it around. At 200 parts per billion, we get about 15 ppb variations in the response. And again, as we go through a series of step changes, we're taking samples and averaging it here, so the time duration's a little bit longer, but we see nice clean step changes going from around 20 ppb up to 170 ppb, up to 330 ppb, and up to 750 ppb. And our variation, our noise levels, our standard deviations are in around that 10 ppb kind of range. So we're able to provide an accurate analysis of the sulfur dioxide concentration in that stream down into the ppb levels with this version of the device. These were all process configurations for the analyzer. So we also, if you're looking to do these sorts of analysis in the lab, Adam provides a laboratory version of it. You can see a sample bomb or a cylinder sitting over here, a laboratory version. One of the more innovative or the most innovative analyzer on the market for doing both total sulfur and total nitrogen. Remember we said that nitrogen could be an interference. Well, we also, if we sometimes want to be able to measure it, especially if we're interested in things like nitrogen content in my liquid hydrocarbons. And so the lab version of this analyzer is configured to do both the total sulfur and the total nitrogen applications. Fantastic analytical performance, very high dynamic range. And again, this comes down to the linearity that you get because of that Excimer light source. Again, labs or liquids or gases all run on the same devices, can run with either air or oxygen, depending on detection limits we're looking at, and of course, full data communications and compatibility with any kind of laboratory information system that you're using. That kind of wraps me up on what I was going to say about the analyzer. I'll come back always to a little bit about Insight and the products that we work with. So, you know, Atom is certainly one of them, and we're proud to work with them. On the, you know, as Teresa mentioned at the beginning, she mentioned Process Insights. So Process Insights has a number of divisions to it. And so we previously gave a presentation about the COSA Zentar BTU analyzers, but also in their realm are these alpha omega percent oxygen analyzers. And there's another one on here. Where you go? I'm missing one. I'm probably going to get fired by these guys because I don't think I put them on the slide for one of their other product lines. Well, the COSA has a Zentar product lines as well, which say moisture liquids analyzers. Oh, and Extrel. Process Instruments. Extrel's been around for a long time. Probably the most well-known process mass spectroscopy company. When I started my career doing mass spec, and Extrel was around then and were the experts. And they've been Extrel, they went into ABB, were purchased by ABB, went back out on their own, and are now in the Process Instruments fold. I'll be doing one of these presentations. Actually, I'm doing a couple presentations next week. One of them is a special session we're doing with JP3 on chemometrics. And then we'll also be doing on the same day, because I love speaking so much, a couple of the Amitech products, the Universal Analyzers distillation probes and the Barbon Analytical oxygen analyzers. So those will both be happening Thursday of next week. We do these webinars, as I'm sure a bunch of you are aware, on pretty much a weekly basis. We try to hit different product lines along the way. And during the course of that, I think that after the Barbon and Universal one, we're going to do the Hawk Praetorian fiber connections for protecting conveyor belts and pipelines. Yeah. So again, we'll be hitting a number of subjects along the way. I always like at this point to, of course, thank everybody for attending. You know, it's always, if you're going to do some public speaking, you like to have some people here, so thanks for showing up. Thanks for attending here. Upcoming webinars, Barbon oxygen and universal distillation probes, and then the Hawk fiber optic products. And then I think the one after that, I might be doing some stuff about one of our own, or some of our own products as well. I usually finish this off because I'm quite proud of our systems integration capabilities. This little animated thing is just going to pop a bunch of systems that we've done in the recent times, and whether it's composite samplers or full analyzer buildings or big analyzer back pans with auto samplers. Like I said, we're pretty happy to do just about any kind of systems integration. Randy Howard from Amitech used to joke that when I public speak, I suck all the air out of the room because I just talk and talk and talk. So I probably didn't leave you guys much time for questions. If you do have any, I'd be happy to take them right now. Just to mention, I guess our website has been updated now, and we're continuously in the process of updating it. Jaden's on here. Jaden's our digital marketing person, and Chelsea Dalzell's on here. She provides some input to our digital marketing group. So if there's anything you'd like to see on there, let us know. We're constantly changing, improving, and growing, I think. So we're also going to be launching our web store soon, which will have some of the products that we manufacture as well as a bunch of our spare parts. So again, thanks everybody so much, and have a fantastic day.